Okay, let's take a look at some problems from Chapter 11 to help us talk about conservation of angular momentum. This is problem 63 in the book. It has a ball being tossed at a child who is on a merry-go-round. It's tossed by a friend, so we can assume the child in question is not being victimized or bullied in some way, but this is in fact some kind of friendly game in which you throw balls at people at merry-go-rounds. I don't know. I haven't been on a playground in a while. Maybe it's a thing. Um, and so the question is asking, what is the angular speed of the merry-go-round just after the ball is caught? Apparently the child is firmly adhered to the merry-go-round, so child catches ball, and then because the ball was moving, the child will start moving, and because the child is attached firmly to the merry-go-round will begin to rotate. So, we need to ask kind of, what has angular momentum here? And just like the really annoying problem that nobody liked on part 1 of the problem set, the idea is that the ball has angular momentum here. And that we have something moving about an axis, not around an axis. So because the ball is not going directly towards the axis or away from the axis, we consider it as moving about the axis. And so what do we use? We use this definition for L, that we have mRV sine phi. And I'm going to use sine phi because the question we have to kind of ask ourselves as we're looking at this problem, these two angles, are these the same angle? I'm going to blow the spoiler horn here and say no, they're not. I didn't actually blow the spoiler horn, sorry. There's a podcast I watched that involves a spoiler horn. If we look at this, here's how we know these are not the same angle. So here is my vector r, and v is going to be going off like this if I put them tail to tail. So this is phi, the angle between them. This is theta. Sine theta and sine phi are definitely different things. This statement is, what we're looking at. Sine of 90 plus theta is not sine of theta. In fact, it's the opposite of cos theta. But more importantly, if we look at this, so ignore this stuff for a second. If I draw over here, here is v. And so what I can ask is kind of the same idea. R is in a good direction, so let's look at this as mr. Wow, didn't mean to make that as a subscript. mrv perp. So the component of v that's perpendicular is not this component, but is rather this component, which is v cos theta. And so physically, this idea of perpendicular velocity, perpendicular force for torques, that is physically accurate, even if the sine and cosine bit gets flopped around. So this mrv sine phi is going to be mrv cos theta. And so if we look at this as conservation of angular momentum, we're going to have, I should specify that this is the mass of the ball. So mrv cos theta is going to be equal to whatever we have rotating, which is the eye of the merry-go-round plus a term from the kid. So using this, is that on my screen or not? Oh, it's a backslash. Whoops. I can solve for omega. It is mb rv cos theta by I plus mcr squared. And if you put in numbers, it's like 0.07 rad per second. So this is just one good example of kind of a situation where you have angular momentum about an axis as opposed to kind of the more traditional around an axis. Now, the other problem we want to look at is number 66. And I already forget what I was going to say about this, so we're just going to do it and hope that I don't do it wrong. So the premise of the problem is that you have a block which slides down and strikes a rod, which has some mass, some length, and then we want to know through what angle it pivots before momentarily stopping. So I'm going to choose to look at this through two lenses. So I'm going to do this second part of the problem where it's kind of going from down here to up here and stopping. So moving to stopping. I want to do conservation of energy. And this first bit of the problem, which kind of addressed how fast is it moving? How fast it move? No. Is it moving? I want to address this from conservation of angular momentum. Which in turn is going to require me to do conservation of energy one more time. So, first order of business. How fast is the block going right before it strikes the rod? Well, this is a good old conservation of energy problem. I have mass of the block, GH, my gravitational potential energy up here, is equal to my kinetic energy right before I strike the rod. So, good old V naught is equal to root 2GH. A good old answer that never quite goes away. And I really should have had a calculator or something, but whatever, we'll just use this. Square root of 2 times 10 times 0.2. Already not going to be the answer in the back of the book, but there isn't a back of the book anyways. Oh, that was really easy. I probably didn't need a calculator for that. Alright, so next question. I take this. What does this tell me about the initial angular momentum? Well, here is V. Here is R. If I make things actually thinnish, as opposed to finish. It's a bad joke, I am Finnish. Anyway, I have MRV sine theta. Sine theta is just going to be 1 because they're perpendicular. So my initial angular momentum will just be MRV naught. That's M block, and let me try that again. This will be M block. R will be L rod, which is the only L, so we may as well leave that. And V naught is what I just solved for. And so this will be 0.05 times 0.4 times 2, which is that. And that's kilograms meters per second. Squared per second. Right, because it's angular momentum. So, then I need to figure out what the final angular velocity of the rod block conglomerate is. So L final, since I now have a rigid body, will be I of the rod plus a nice ml squared term for the block times omega. I want omega because I'm then going to talk about my rotational kinetic energy, which gets used up. So, this would tell me that this is equal to L initial, which is equal to, I know from all of the previous times we've done this, that a rod about its endpoint is 1/3 ml squared. We have M block, L squared. Have to be careful to keep those separate. And so we have, omega equals what I will just call, I probably should not use, let's change these all to uppercase L's, so as not to confuse them with the length, which probably would have been easier to change because there's only the one length and there are many angular momenta as I've done this problem. So since Li and Lf are both just L, we'll just do that, and then we have a 1/3 M rod, L rod squared, M block, L rod squared, and then we need numbers, I guess. So this is 0.04 divided by this huge thing, 1/3 times 0.1 times 0.4 plus 0.05 times 0.4 squared, and we hope that I didn't make any typos. Doesn't look like it. Hey! 1.875 rads per second. And we are almost done, but not quite. Oh god. There's even one more step than I thought there was. So now, conservation of energy. Conservation of energy says that 1/2 I omega squared, the rotational kinetic energy I initially had, because I'm thinking of this thing entirely as rotating about this pivot point. The pivot point is not moving, so there's no translational kinetic energy. This is going to be equal to mgh. And this is such an inelegant way to solve the problem at this point, because I should have figured out what h was in terms of theta, but I guess we'll do that step next. So h is equal to I omega squared by 2mg. Oh, nope, this is going to be awkward. This was a bad idea. And let's see if you can figure out what this bad idea is before I draw it on here. If you thought, because you don't really know what m is in this context, you are correct. So, I guess it's fair to think that it's just the total mass. Because you're right, because everything raises a distance h. The center of the rod raises a distance h, and the mass raises a distance h. Rises, I guess, is probably actually the grammatically correct word. Rises a distance h. So, yeah, I can just use the total mass. Alright, never mind. Back on track. So h looks like I, again, in this case, is this total I, which I have sloppily not used. So m rod L squared plus m block L squared omega squared, which we just found, and then 2 m rod m block G. And so this is something. We'll figure this out in a second. Oh, let's maybe not leave that right there. Okay. We have a third times, I'm already forgetting what some of these values are. 0.1 times 0.4 squared plus 0.05, which I remembered for some unknown reason, times 0.4 squared, times this new thing that we just calculated, which I scrolled off the screen kind of preemptively, 1.875 squared, divided by this whole thing, which doesn't need two parentheses because it's all multiplication, but I'm going to do it anyway, is 0.1 plus 0.05, because apparently I can't do basic algebra in my head, equals, darn it, where did I, that was anticlimactic. Let's try that again. Turns out that if you do this wrong, it just doesn't like to treat things as a formula, which kind of complicates things. Although I may have actually messed up the formula, which could have explained that, but you never know. I'm sure this commentary is extremely useful. But you know, that's life. Unuseful commentary. Is it 0.05 or 0.005? 0.05. Alright, so I'll do the math this time, since I had the opportunity to correct my error, and in doing so created much more math than I needed to. There we go. Alright, so it goes up 0.0156 meters, which means that we have L rod, theta, 0.0156 meters. So, L minus H is equal to L cos theta. So L minus H by L, because, again, this bit here, L cos theta, is equal to cos theta. So theta is arc cos L minus H by L. I hope that's actually arc cos. I never really remember if that's a thing or not. 0.4, nope, parentheses, 0.4 minus 0.0156, close parentheses, divided by 0.4, is Does our coast not have two C's? Our coast definitely has two C's. We'll try that again. 0.4 minus 0.0156 divided by 0.4. Find a real calculator. I'm convinced it's probably right. Anyway, hopefully this long and rambly and, fretting thing is useful in terms of solving these two problems. This has, again, angular momentum that's kind of, not in a circle. This one has conservation of so many things one after the other. Good luck.